So I'm going to be speaking about joint work with Marco Gabardi, Audra McMillan, and Jayshree Sarathi, who are computer scientists, and Jörg Drechsler, who's a statistical survey methodologist at the IAB Institute for Employment Research in Germany. And basically what we try to do in this work is understand, in finer detail, the relationship between differential privacy and sampling, especially sampling that appears in statistical survey designs. So just so that we're on the same page, give a reminder for differential privacy. So we're interested in looking at randomized algorithms M that operate on some data set of n rows, which we'll call P, standing for population. And I'm going to be like totally agnostic as to what M is going to output. It might be some summary statistics about P. It might be a synthetic data set whose statistical properties are supposed to reflect the same statistical properties of P. Or it might be a statistical or machine learning model capturing information about P. Doesn't matter. We say that M is epsilon differentially private if for all P and P prime differing in the information of one individual, corresponding to one row, and all sets T of possible outcomes, the probability that M of P lands in T is at most an e to the epsilon factor away from that probability when the data set is P prime. So nothing like special or interesting about this definition. It's the one we know and love. I'll just emphasize that we'll focus on pure differential privacy here. We'll demand a strict e to the epsilon multiplicative gap, mostly for simplicity. I think everything I say will more or less translate to other variants like epsilon delta differential privacy. Other thing, again, this is a talk about the interplay between differential privacy and random sampling. And we have some intuition that random sampling is good for privacy. Like if, I'm an individual whose data is like not sampled by an algorithm, I should expect that the output of that algorithm has, little or nothing to do about me. So I should expect to get some privacy. And you can ask like what kinds of privacy guarantees are afforded by the algorithm that just literally samples, say, like an R fraction of the input data set and spits out those records in the clear. Okay, so is this differentially private? Well, turns out the answer is no, not for any finite value of epsilon. And intuitively, the reason is, if you look at the output, these like output Rn records, and you see that, say, like X3 is in the output, then you know with certainty that X3 was in the original data set. Whereas if X3 was not in the original data set, X3 would appear with probability 0 in the output records, which would violate the strict multiplicative e to the epsilon guarantee. Okay, so sampling on its own doesn't guarantee differential privacy. But a really beautiful and important phenomenon that was discovered in the relatively early days of differential privacy was that if you take a differentially private algorithm M and you pre-process it by first taking your original data set P, subsampling something like an R fraction of it, and then putting the subsampled data set into the algorithm, well, it stays DP. And moreover, the DP guarantee improved by a factor of R. So if you sample an R fraction of the data set, the differential privacy guarantee gets smaller. It gets better by a factor of roughly R. Okay. So this was first observed in the setting of sampling roughly an R fraction via Poisson sampling. So sampling each record independently with probability R. Implicitly in this work of cleaners, the phenomenon was later described in more generality in a blog post of Adam Smith and in some subsequent work on private learning by Mull et al. It was also extended to the setting of sampling with replacement, simple random sampling with replacement. And relatively recently, a more general framework for reasoning about the privacy amplification effects of sampling via probabilistic couplings, recovering the results that I talked about so far, was given by Baya et al. All right, so what's privacy amplification so amazing for? Well, first off, sampling a fraction of your population is intrinsic to the design of statistical surveys. Like whenever you conduct a statistical survey, except for the decennial census and things like that are supposed to count everybody in the population, you generally have some like sampling process. You sample a small representative fraction of your population and compute statistics about that sample. Okay, so it's useful to understand what impact sampling can have on privacy. If say, we look at something like the Census Bureau's American Community Survey, where you take your population of all Americans and you sample something like a 1 in 500 fraction of American households, and then every month, and then compute statistics about that. You'd like to understand if the privacy guarantee that you give with respect to the sample translates into an improved privacy guarantee relative to the population that you started with. So another reason is that sampling is just a fundamental and ubiquitous primitive in the design of algorithms, and in particular, differentially private algorithms. So one striking example is in optimization and machine learning. Stochastic gradient descent, where you sample small subsets of your data set and then compute gradients with respect to those small samples, give you better privacy for each step of the subsampled algorithm. And analyzing each of your iterations in this way gives you, state-of-the-art guarantees on convergence rates and how those are affected in terms of privacy parameters. So for these reasons, in implementations of differential privacy, for instance, in the private sharing interface and DP creator that are part of the OpenDP project, these frameworks ask you if your data set that you're working with can be interpreted as a random sample from some larger population. And if so, you can set your privacy budgets and the resulting sorts of guarantees accordingly. So unfortunately, I'm lying to you a little bit in the sense that sampling that happens in statistical surveys is usually not simple random sampling, the kind that we are able to analyze using existing frameworks. So Jorg taught me a bunch of words like cluster sampling, stratified sampling, systematic sampling, probability proportional to size sampling, multi-stage sampling, where you combine sampling, different kinds of sampling designs in a hierarchical fashion. And these are the kinds of more general complex design methodologies that are used in real statistical surveys. So the question that we asked and tried to take some steps toward answering is, can we analyze the privacy amplification, or in many cases, non-amplification guarantees of these more complex sampling designs that are used throughout survey statistics? And a related question to this is, in cases where existing survey designs do not amplify privacy, can we modify them, ideally in small and sort of palatable ways to the users of these things, so as to actually amplify privacy in the way that we expect? Okay, so those are the two main motivating questions. And throughout this talk, I want to tell you some of the, hint at least some of the technical ideas that we use to try to answer these questions in different settings. Okay. So here's the outline for the rest of the talk. I'm going to talk about our general framework for reasoning about privacy and more complex privacy amplification and more complex designs. I'll try to start with the basics and try to illustrate a couple of the technical tools that we introduce for reasoning about things like randomized or data-dependent sampling rates that go a little bit beyond simple random sampling. And then I'll talk about some more of these complex designs that are used in practice, like cluster and stratified sampling. Okay, so here's our framework. So suppose we have some data set H, which is not the data set that we're trying to analyze with differential privacy per se. So H you want to think of as representing historic or auxiliary information. Say, the results of past ACSs or past decennial censuses or something like that, which inform us about the data set that we're actually interested in analyzing. It might have some of the same statistical properties, but is not necessarily the same data set. And based on this historic or auxiliary information, we come up with a sampling design, which is basically a rule, so a way to assign probabilities to different samples that we could have of the population that we're actually interested in. Okay, so once we have the sampling design, which is a function of the historic data, We'll apply it to the data that we're actually interested in, to P. We'll come up with some subsample, and we'll pass it into a differentially private algorithm. Okay, and the question I want to ask is, what are the privacy guarantees of this resulting composed algorithm composed with C? So I'm gonna make some simplifying assumptions. So I spent 30 seconds talking to you about historic or auxiliary data. I'm gonna make the simplifying assumption that the historic data is just the population that you're interested in. So you're totally welcome to fight me on this. I guess it's the motivation for it is mostly simplicity. If you're totally uninformed about how the sampling design might depend on the population, one thing to do is just assume that it depends on that it's the population itself. Of course, there are other totally reasonable things to consider, like if the historic information was the output of another differentially private data release, or of otherwise public information that doesn't have any privacy implications for the P that you actually care about. But with that assumption in place, we're thinking of this end-to-end process as only a function of the population P. The problem formulation is as follows. Given this function C that tells you how to sample records from P, and a starting epsilon differentially private algorithm M, what's the best epsilon prime differential privacy guarantee that you can prove for this resulting end-to-end process? Okay, and here I want to emphasize that I'm looking at worst case epsilon prime over mechanisms M. Okay, so I want to analyze this for the worst possible epsilon DP algorithms M. All right, so just so that we're sort of on the same page with the framework, if we look to the settings that we already understand, simple random sampling, say without replacement, if we take C of P to be the design where you sample some constant, independent of the data, M, number of records, uniformly without replacement, then the results we already saw showed that M composed with C is always epsilon prime differentially private, for epsilon prime being this expression, log of 1 plus M over N times e to the epsilon minus 1. Okay, and for small values of epsilon, you can use the approximations, e to the x is basically 1 plus x, log of 1 plus x is basically s, to argue that this is basically M over N times epsilon. So if you're sampling an M over N fraction, an R fraction of the data set, you get amplification as we expected by a factor of R. Okay, so again, thing I want to emphasize here is that M in this result has to not depend on P. It's a constant independent of P. Okay, so that's the result we know and love. I want to talk about trying to extend this just a little bit to settings where sample sizes are not necessarily independent of the data or not necessarily even deterministic. So here's a slightly more general setting. So if instead of having M, the number of samples, be independent of the data set, suppose I want to sample F of P records without replacement, where F is some function depending on the population P. Okay. So if we're interested in trying to prove something about the privacy amplification guarantees of this, one observation is that if F is some deterministic function, F itself should not be too sensitive. It shouldn't depend too much on changing one row of the data set P. Okay, and the reason for this is, suppose you had two neighboring populations, and suppose F of P was some value M on one population and F of P prime was M plus delta for, say, some reasonably big delta on the neighboring population. Then if I look at the bad mechanism M, which is the canonical noise adding mechanism for differential privacy, you add Laplace noise scale to 1 over epsilon, then the privacy guarantee of this thing is delta times epsilon. Okay, so if delta is bigger than 1, it actually gets worse by a factor of delta. Again, thinking of this worst case choice of M. Okay, so that's intuitive, but kind of bad news. So here's another somewhat more subtle issue that can happen. So consider another scenario where if instead of having a deterministic number m of cases that we want to sample, we have some constant rate r, some like fraction of data sets that we want to sample. Now, in general, r times n, the number of records that we're interested in sampling, might not be an integer. Okay, so we're going to want to sample, f of p being some integer number of records that's like close to r times n. Okay, and like one simple approach to doing this is to just like deterministically round r times n to the nearest integer. But I want to argue that this, in fact, is not good for privacy. So, or at least it doesn't amplify privacy in the way that you might expect. So again, if you consider neighboring populations p and p prime, and let's say I have some target sampling rate, which is like 1/10, and let's say the size of p is 14, so something that you would round down to 1, and the neighboring data set is p prime, which is something that you would round up to 2. Okay, then if you again consider the algorithm that adds Laplace noise at scale 1/epsilon, well, in one case, I'm adding like Laplace noise at scale 1/epsilon to 1 record and Laplace noise at scale 1/epsilon to 2 records. So the privacy that I get is still just epsilon. There's no amplification here. Okay, so that's sort of bad news. But it turns out in this scenario, there's a simple fix to this, which is a technique that's kind of like ubiquitous in algorithms, which is to do randomized rounding. So if instead of rounding Rn deterministically to the nearest integer, if I let p be the fractional part of r times n, and I choose a number of cases, which is the floor of r times n with probability p and the ceiling of r times n with probability 1 minus p, then it turns out that this recovers basically up to a constant factor the sampling guarantee, the amplification guarantee that you expect. Okay, you get epsilon prime is at most constant 6 times r times epsilon, and 6 can probably be improved. Okay, so I'm like totally running out of time. So I'll just like skip a bunch of stuff. We also, consider randomized data independent sampling rates. Improve some stuff about this. I'm going to get on to these more complex sampling designs that I promise, in particular, is clustered and stratified sampling designs. Okay, so in cluster sampling, you have your population P, which is partitioned into some number K of clusters. Say I want to, do some survey about all Americans, and I cluster them into states. And cluster sampling, I want to sample everybody who lives in a good state. I mean, sample a random sample of C clusters for some number C. And states are actually not such a great example of this, because for this to work, I want the clusters to be internally heterogeneous, but mutually homogeneous. So sampling everybody from some small number of clusters will still be representative of the country as a whole. And what we show is that while cluster sampling doesn't make privacy worse, it doesn't actually make privacy better. Okay, so this is not a super nice expression, but if you let n max be the size of the largest cluster, if the size of the largest cluster is small, we prove a lower bound, an impossibility result, saying that epsilon prime needs to be basically about as big as you would expect in the simple random sampling case. But if n max is large, if you have some big clusters, then basically you get no amplification. Epsilon prime needs to be as big as the epsilon that you started with. And the intuition for this is, if you have a large cluster, and some ability to determine whether that large cluster was included in your sample, then you don't have this phenomenon of secrecy of the sample. You can reconstruct what the set of states that you sampled was, and in doing so, you get basically for everybody who was, for all of the clusters that were actually sampled, you basically get the same privacy guarantee as the original mechanism had on those clusters. And we have a formulation of this in terms of hypothesis testing that you can use to prove more general results for other sampling designs. So I guess I'll mostly skip what I wanted to say about stratified sampling. But wanted to wrap up with some concluding thoughts. So the negative results, like these non-amplification results for cluster sampling, they're not really specific to cluster sampling. We give a general hypothesis testing framework. Basically, if you have a procedure for inverting the identity of the things that you sampled, for violating secrecy of the sample, well, then you get non-amplification results. We identified a couple of general ways in which this entire pipeline can fail to achieve amplification. There's some situations where with certainty that some element is going to be included in your sample, in which case privacy for that sample is not going to amplify. There are settings where inclusion is extremely data dependent. The function used to choose a number of subsamples might be highly sensitive. Or these other settings like in cluster sampling where inclusion, secrecy of the sample doesn't happen because membership is invertible. Nevertheless, I still feel like there's some reason for optimism and in further investigation of this topic. Randomized rounding is a very simple tweak that apparently survey statisticians are open to using and sometimes do use. And I guess in the interest of time, I'll just leave these open directions up here. Thanks.
Thank you.